Xraster is a multidimensional raster analysis plugin for QGIS. This presentation will showcase an example of analyzing multidimensional data of the Arctic from the Copernicus Marine Data Store, describing key marine environmental parameters such as water temperature and salinity, ocean currents, as well as the concentration and thickness of the ice cover. We will focus our interests on two key aspects of the hydrology of the Arctic Ocean: thermohaline circulation and changes in ice cover. Thermohaline circulation originates in polar regions where incoming surface waters cool down and subsequently form ice. As salt is expelled during the freezing process, the remaining water becomes denser and sinks, creating deep ocean currents that transport these waters toward the equator. Disruptions to this mechanism due to global warming could have far-reaching consequences. Changes in ice cover involve not only variations in the extent of sea ice, but also changes in its mass, which requires consideration of both ice concentration and thickness data. Of course, this is not a comprehensive analysis of these phenomena. The goal is solely to demonstrate how Xraster enables this type of analysis. The study uses Xraster version 02, which allows for improved analysis and visualization of polar regions by accounting for the actual surface areas of raster cells and applying the polar stereographic projection. We will use the Arctic Ocean Physics Reanalysis data available in the Copernicus Marine Data Store. The method for semi-automatically downloading this data using the Copernicus Marine Toolbox with the Python Application Programming Interface, API, is clearly and thoroughly described on their website. We will utilize a dataset containing monthly average variables for the entire Arctic Ocean. 3 working subsets will be created, including the following variables: sea ice area fraction, sea ice thickness, seawater salinity, seawater potential temperature, eastward and northward seawater velocity. The first subset includes all variables for the Arctic region shown in the figure, covering 40 depth levels from 0 to 4,000 meters in the year 2023, averaged over 12 months. Please note that the dataset has the following dimensions: depth, longitude, latitude, and time. The size of this subset, like the others, is approximately 2 to 3 gigabytes. The second subset is a smaller portion of the first, limited to the area between Greenland and Iceland. It also contains monthly averages, but for the period from 1991 to 2023. This subset does not include ice data. The last subset contains only surface data on ice concentration and thickness. These are also monthly averages from 1991 to 2023, covering the entire Arctic region. Since the data pertains only to the surface, it is a 3-dimensional dataset with the following dimensions: time, latitude, and longitude. We start by launching the Xraster plugin and loading the first dataset. Since we will be visualizing the data using a stereographic projection, we will reduce the spatial resolution to improve performance. The graphical interface requires longer processing times at higher resolutions. We will reduce the x-axis resolution by a factor of 5 and the y-axis resolution by a factor of 2 ton. To apply these changes, we enter the values in the x and y fields and click the Change Spatial Resolution button. We can check the changes by pressing the Dataset Info button. We can see that the resolution has been changed to 160 rows on the y-axis and 176 columns on the x-axis. Now we proceed to the Subset tab. We will start by creating 3 maps showing the distribution of temperature, salinity, and current velocity. Since the surface water layer is influenced by the atmosphere, the maps will be generated for a depth of 300 meters. We begin with the temperature map for March. We go to the Figures tab and select North Polar Stereo and Coastline. Then we click Plot. To improve the temperature scale, we will limit it from the bottom to -2 degrees. We will create a similar map for salinity. We will also create a current velocity map, but this time it will represent the maximum values for the entire year. To do this, we need to create an expression in the Calculate field that computes the current velocity from its components along the x and y axes. First, we reset the current variable by multiplying it by 0. Then we enter the expression. The created subset contains 12 maps, one for each month. To generate the maximum value map, we go to the Statistics tab, select Max, and click Plot. The generated map shows the distribution of current velocity at a depth of 300 meters. We can observe that the distribution of temperature and salinity corresponds to the distribution of currents. We will analyze how temperature and salinity have changed at the point where the cooling of warmer waters transported from the south should occur. We select a point with a relatively strong current compared to the surrounding area. We go to the Subset tab and define the data at this point for the entire depth and time range. Next, we go to the Figures tab. In the Figure Type field, we have Depth Time Cross-Section. Then we click Plot. Just like before, we will change the temperature scale and also adjust the depth range to 1,500 meters. We can see the sinking of cold waters with temperatures below 0 from March to May. We will create a similar plot for salinity. We will adjust the salinity scale to emphasize the structure of its distribution. We can see that the highest salinity at depths of several hundred meters occurred in January and February. We can now clearly see how temperature and salinity changed at the analyzed point in 2023. Now we will analyze how the current between Greenland and Iceland, which is a component of the thermohaline circulation, changed from 1991 to 2023. We select the coordinates of the point. We input data for the analyzed area between Greenland and Iceland, including monthly averages for the entire analyzed period. We go to the Subset tab. We define the subset for the selected point at a depth of 300 meters. In the Calculate field, we enter the expression again to calculate the current speed from its components. We go to the Figure tab and use the Plot function to create a graph showing how the current changed over time. The current speed varied from 30 to 13 centimeters per second. The label on the vertical axis can, of course, be changed, It originally indicated salinity, but it has been replaced by the current speed in the calculate field. We will check how the current speed changes from month to month. To do this, we will modify our data subset from the point to a small slice of data in space to allow for grouping. We go to the Group by Time tab, select Grouping by Months with the average value, press Run, and then plot the time series using Plot. We can see that the maximum current values occur from January to March. We will limit our subset to these months. We go back to the Group by Time tab, select Grouping by Years, press Run, and then plot the time series of the average current speeds for each year. We can see that the average current speed showed a clear decreasing trend until 2019, but then it seems that this process was halted. We will now proceed with the analysis of changes in the ice cover. We will input data describing the concentration and thickness of ice for each month from 1991 to 2023 for the entire Arctic region. Due to the fact that the raster resolution on the x-axis is over 2,000 pixels, we will reduce it 12-fold, and on the y-axis, 2-fold. We can see the changes after pressing the Dataset Info key. Additionally, we will input a variable describing the raster cell sizes in square kilometers. We will use it in area calculations. Press the lat-long area variable key and confirm the creation of the variable by clicking the Dataset Info key again. Now we can go to the Subset tab and create a complete data subset to determine the ice coverage area for each month. For this purpose, we will multiply the ice concentration value in each cell by its area in square kilometers. We will use the previously created variable km². Press the OK key. Go to the Statistics tab and create a time summary for spatial summary statistics, select Sum, and press the key. We have obtained a chart showing how the ice area changed from month to month in tens of millions of square kilometers. From this chart, we can determine the moments with the largest and smallest ice coverage. We can see that the maximum ice coverage occurred in March 1997 and the minimum in September 2012. We will create maps of ice distribution for these two dates. Go to the Subset tab and select the first date. Restore the variable to its original state. Click OK, then go to the Figures map and click Plot. First, select North Polar Stereo and Coastline to create the map in a stereographic projection. We have obtained a map of the maximum ice coverage from 1993 to 2023. Now, we will create a map for the minimum ice coverage. Since it is difficult to determine the trend of changes from the created time series plot, we will examine the changes that occur year by year in the months with the maximum and minimum ice coverage. We will use the ice volume in cubic kilometers, utilizing the variable for ice thickness. First, we will determine the ice volume for each cell by multiplying the ice concentration by the cell area and the ice thickness converted to kilometers. Since we will be grouping the data by month, by summing it, to get the monthly average, we need to divide the sum by 33. We press OK. We go to the Group by Time tab, select Months and Sum as the statistic, click Run, and then click Plot. We can see that the highest average ice volume occurs in April, reaching over 20,000 cubic kilometers, while the lowest is in September, below 8,000 cubic kilometers. We will analyze how the ice volume changes in these 2 months for the entire Arctic over the analyzed 33-year period. First, we create a new subset in the Subset tab, specifically for April. Since we will be grouping by years, we only have 1 month to sum per year, so we don't need to divide the sum by their multiples. We go to the Group by Time tab, select Year and Sum as the statistic, click Run, and then click Plot. We will create a similar plot for September. We can see that for both months, there is a clear trend of decreasing ice cover volume, with a temporary increase around the year 2015. The small differences in values between the shown results and the published analysis may stem from 2 factors. First, our data does not account for the entire ice cover, as it is cut off at the 50th parallel and possibly also geographically. Second, the analysis is based on monthly averages rather than daily data, which naturally impacts the final results. Nevertheless, the variability trends in the graphs are consistent with the published results. This presentation is not a scientific study, but rather demonstrates how Xraster can be used in the analysis of polar regions data. Information about the program can be found in the About tab.